evolution of technology, like, it doesn't happen automatically. The evolution of technology and evolution of humanity, only happens if somebody does something about it.
There are so many things on Earth that we can't see or haven't seen before. There's so many things that are happening that we haven't been able to observe before.
ICEYE has developed a completely unique technology. It's a synthetic aperture radar system mounted on a small satellite and allows us to see through clouds and darkness any place around the globe.
Now, with the ability to rapidly revisit, looking at a location in the exact same time and place, you're able to develop a clear picture, a clear understanding of what is going on, what is the pattern of life.
The thing that's new about this is it's a level of persistent information, persistent imaging that the planet has never seen before.
This situational awareness is something that I think people have only kind of dreamed about in the past. I hear you have created the Holy Grail several times a month.
The usual conversation is, well, you can't do that. We've never done that before. That's sort of crazy, right?
We've gotten feedback about how we're revolutionizing their ability to respond and how, they went into it not thinking it was possible, and then it is possible, and that shocks them.
ICEYE's system is really important because it gives scientists and governments a tool that they have never had before.
It's a new way to observe the life on Earth because it's the first time that really we can reach anywhere and anytime.
Hi, I'm Tom Ager, and we're going to begin our SAR talks today with an overview of synthetic aperture radar. So synthetic aperture radar is an imaging technique that uses radar pulses to image through clouds. We live on a cloud-shrouded planet, so SAR is a very useful imaging technique for this place. SAR can also image through darkness. We do not need reflected sunlight, and the planet is dark half the time. And in the polar regions, darkness lasts for many months. So SAR's heritage is that it used to be isolated to secret programs, intelligence agencies in the United States, where I had my career, for example, and in other countries. Also very large civil programs, NASA, the European Space Agency, the Canadian Space Agency, the German Space Agency. And just over a decade ago, a few very capable SAR satellites were launched. TerraSAR-X from Germany, RadarSat-2 from Canada, and Cosmos SkyMed from Italy. These satellites, very capable systems of very high resolution that provide open and shareable images. They are, though, built with government commercial partnerships, and they require large government investments, and they are large, massive satellites, over 1,000 kilograms. The ICEYE revolution is that we have a small SAR satellite constellation that's funded by venture capital funds. There's no support from large government programs. They are much cheaper to develop, and they can be built much quicker. Both the hardware and the software development is faster. And the mass is only about 100 kilograms or so, much, much smaller and lighter. So we have a very brief intro to SAR to begin with. We know we're going to use radar pulses to image the ground. We send discrete pulses of radar to the ground, and we measure the range to the ground and the strength of the echo. When the pulse hits the ground, it reflects in many directions. The part that comes back to the antenna is called the backscatter. And if the backscatter is strong, that's a bright pixel. If it's weak, that's a dark pixel. The pulse repetition frequency is the rate at which we send our pulses to the ground. For an aircraft, we send many hundreds of pulses to the ground every second. For a spacecraft, the pulse repetition frequency might be 2,000 or 3,000 pulses per second. For optical cameras, looking down to the ground gives you the best resolution. For SAR, that does not work. SAR measures range. So if we illuminated the ground vertically, we could have 2 points with exactly the same range in different places. So those points for a given line would be placed at the same pixel location on the image, and it just wouldn't work. So for SAR, we have to be side-looking. In this configuration, every point on the ground has a discrete range, and therefore all of the pixels would be in different locations based on their range. So given this side-looking illumination, we have here a description of the radar imaging angles. We're flying in this direction. Most SARs illuminate broadside, that is 90 degrees to the flight path. Some SAR sensors can squint, that is, they can illuminate the ground forward or behind broadside. Although right now that's kind of rare. That gives you more flexibility in collection if you can squint. The grazing angle is the angle between the line of sight ray and the tangent to the ground. The incidence angle is the angle between the line of sight ray and the local vertical. Now, different people in the SAR community use these two different measures. Some say incidence angle, some say grazing angle. And you have to be careful when someone tells you the look angle. The word look angle itself is rather vague. Incidence angle means something specific, and so does grazing angle. Notice the two of them form a right angle. So a 30-degree grazing angle is equivalent to a 60-degree incidence angle. So when to build up a large area on the ground, we send our pulses, usually broadside, move along in the flight direction, and accumulate a large area or strip along the ground surface. The illumination to the ground is called the slant range. The dimension along the flight path is called the azimuth dimension, and the range along the ground surface is called the ground range. So we have radar dimensions in azimuth and ground range. So the two resolutions of radar are called azimuth resolution and range resolution. The one that really matters to us is the ground range resolution because we build our images on the ground. So why do we call it synthetic aperture radar? The special aspect of SAR is that we use coherent illumination. The sunlight, the photons emitted from the sun, consist of many different wavelengths of light. Blue light, green light, ultraviolet light, infrared light, and those photons or wavelengths are all offset from each other. So the illumination from the sun is chaos. The illumination from a radar or from a laser is coherent. That is, they only send out one wavelength of light. Could be red light for a laser, or 3 centimeter microwave illumination from a radar, like ICEYE. We use what's called X-band microwaves, and those wavelengths are 3 centimeters long. They're also always in phase with each other, up and down, in the same motion, sort of like synchronized swimmers. So coherent illumination is controlled and consistent illumination of a single wavelength, and that enables SAR imaging. So with SAR, because it's coherent, we can measure the phase of our return. Phase merely refers to the state of the wave when it reflects off and on, when it comes back to the antenna. Is it at its peak, a trough, or somewhere in between? So we can see in this illustration, we measure phase very, very precisely. In fact, many of you probably were aware a few years ago some brilliant scientists won the Nobel Prize for measuring Einstein's gravity waves. They were able to do that by measuring phase differences. So phase is the most precise measurements we can make, and is the basis of radar imaging. So we use a small antenna to send our pulses and to measure range, brightness, phase for every echo. So as we move along in the flight direction, we send a pulse, measure the echo, move a little bit, send a pulse, measure the echo, move a little bit, send a pulse, measure the echo. And every time we do that, we can measure brightness, phase, and range. So in the end, we have this accumulation of data for all of the echoes accumulated in our flight direction. We use that data to form images on the ground with sophisticated software. So our ground processors use the radar measurements to build images. The synthetic aperture is the length that the antenna moved during the illumination period. So if I begin to send my pulses over here, I'm going to send thousands of pulses every second to the ground and accumulate a big image. The synthetic aperture is the length that the antenna traveled during the illumination time. So here we can see we started to image on the left side, this yellow point on the ground, and we moved along with a big wide beam on the ground and illuminated that point. And the distance that the antenna traveled is called the synthetic aperture. So we use a very small antenna, perhaps only 3 meters long, to create a synthetic aperture by moving along and accumulating all of these echo measurements from discrete locations. Azimuth resolution improves as the synthetic aperture gets longer. So it gets better as L gets longer. So the synthetic aperture determines azimuth resolution in the flight direction. The other dimension of a SAR image is the range dimension. And the resolution in the range dimension is a function of the structure of the pulse we send to the ground. In this illustration, we can see that we chirp the pulse. That is, we vary the frequency of the pulse in its length. You can see here the frequency of this pulse is changing. It's not just a single frequency. It changes during the pulse length. We call it a chirped pulse because if you do this to a sound wave, it sounds like a bird's chirp. So in SAR illumination, we chirp our pulses, and that allows us to have very high range resolution. The pulse bandwidth is the amount that we change the frequency of the pulse during its length. So we can see here it's changing, and for ICEYE, our Generation 3 satellite is going to have a 600 megahertz chirped pulse. That is, we're changing the frequency of the pulse by 600 megahertz during its illumination time. Right now, pulses of 300 megahertz are common, and a 300 megahertz pulse will give you a half a meter resolution in the slant range direction, or about a meter on the ground. With 600 megahertz, that's going to be a quarter meter in the slant range direction. So it's important to realize that azimuth and range resolution are independent of each other. Azimuth resolution is a function of the synthetic aperture length, how wide our beam was down on the ground, how long we illuminated this object as we moved along, and range resolution is a function of how much we chirped that pulse when we sent it down in the range direction. Both are capable of quarter meter resolution, and both are independent of distance. That's actually an amazing statement. With optical, of course, as you move your camera further away, resolution degrades. With SAR, that doesn't happen. In fact, in the early days of radar imaging, SAR was developed in the early 1950s. In the United States, in the early 1960s, this fact that is independent of distance was actually a secret fact in those days. SAR, though, is very sensitive to distance because as it moves away from the ground, the signal strength weakens tremendously. So SAR antennas have to be very sensitive to measure the weak reflections, but resolution itself does not degrade with distance. The commercial SARs in a few years, not too long from now, will achieve the practical maximum of resolution in both azimuth and range. So if a SAR image then measures brightness and phase, we can produce two types of SAR images. Amplitude images, which you're used to viewing, which has brightness information, and a phase image, which has a phase measurement for every pixel. And while in this illustration, the phase information may seem random and chaotic, it is not. It is very, very useful, and with this information, we can create some special products, which we'll talk about in our later talks. So what I want to emphasize here is the natural product of SAR illumination is an amplitude image and a phase image, both. And the phase is precise and valuable. The combination of the two is called a complex image. Why do we say that? Well, SAR engineers use a mathematical construct called a complex number to store these data, and a complex number has two values. So a SAR pixel is a complex number that has an amplitude value and a phase value. That's the reason we use that term. All you need to understand is that SAR produces this natural complex image with amplitude information and phase information. We'll see how we can use this in later webinars, but I want you to consider right now, if I send you an image for viewing, you're going to get the amplitude pixels only. All of that valuable phase information is thrown away and it's not available to you. So in the coming years, we're going to have to find a way to make phase information easily available and consumable to regular users, not just scientists and engineers. Because without that, the richness of SAR cannot be available to people. I'm sorry to focus on this so much, perhaps, but I want you to realize again, Einstein's gravity waves were measured by phase changes, and that is how SAR works. It measures the little phase changes from all of these discrete pulses we send as we move this antenna along. All of those little discrete phase changes are measured with a precision much, much less than a single wavelength. Astonishing statement. So we talk about SAR resolution. We usually think about spatial resolution, azimuth resolution of the pixels, range resolution, and we saw that one of them's based on the length of the synthetic aperture. The other one's based on the chirp of the pulse, and that's fine. But there's also a phase resolution, and the phase resolution of SAR is much, much less than a single wavelength. We have a number of different imaging modes with SAR. Spot mode is the highest resolution mode, and in this mode, we vary our illumination angle a little bit to image a single area on the ground as we move along. And it's like I shined a spotlight at a single place on the ground. So in spot mode, we get a very long synthetic aperture over a small ground area. So imagine this. We have an antenna 3 meters long, but I'm moving along, sending all of these pulses, and I'm going to illuminate the ground for 10 seconds, even maybe 20 seconds. And that's going to produce for me a synthetic aperture that's over 100 kilometers long. So, using this tiny 3-meter antenna, I can create a synthetic antenna over 100 kilometers long. It's as if I have an antenna in space that long, and that's an astonishing capability, spot mode. The satellite travels at 7.5 kilometers per second in low Earth orbit. So if I image, and this can be done routinely for 10 seconds, I've moved 10 seconds, 7.5 kilometers per second, that's 75 kilometers. 20 seconds, 150 kilometer synthetic antenna. And that can be done right now. Here's a spot example of Helsinki, Finland. And you can see in this image, this, by the way, is a reduced resolution of the full spot image. You can zoom in and see much more detail. You see the great railroad station. You can see all of the urban infrastructure and roads. You can see some forested areas even. You see the port and all of the water. You see ships in the ports. You can see some icebreakers in there, a cruise ship. In strip mode, we send our image, our illumination, usually just broadside, and accumulate our image in this way, building it up, sending our pulses, not changing the illumination direction as we do in spot mode. This gives you a much larger image at reduced resolution, maybe 3 meter resolution instead of less than a meter in spotlight mode. So it's a fixed illumination angle, usually broadside, medium resolution, large, long strips. Here's a strip example of San Francisco, California. You can see at the top the Pacific Ocean, and you see the great ability of SAR to measure texture. Look at all of the wave structure that you can see there. You see the Golden Gate Bridge. You see the built-up urban area of San Francisco. You can see Golden Gate Park, the Presidio Park, the San Bruno Mountains, ships in San Francisco Bay. In scan mode, we get modest resolution, but very large, wide swaths. In this mode, we're going to change the incidence angle as we move along. And very quickly, scan this way, move it a little bit that way, scan over this way, move it out that way. So by changing the incidence angle as we send our pulses to the ground and varying and sweeping the area on the ground a little bit, we get multiple overlapping strips in a single illumination. The cost of this is reduced azimuth resolution, but you get very, very wide areas and very long strips in scan mode. Here's an example scan mode image. This image was taken shortly after that large cargo container was freed. It was blocking the Suez Canal. Here we can see it's 100 kilometers long and it's extremely wide. We're going to zoom in here and see all the detail you can see in this gorgeous image. Look at the topography, how nicely SAR shows topography. You can see all the ships sitting there waiting to get through into the Suez Canal. If you look at the canal itself, you can see the ships lighting up very nicely, all of them going through the canal. Then let's move along, and now we can see the city of Suez. Again, the ships in the canal are lighting up their metal and their bright SAR signatures. Here is Great Bitter Lakes, and some ships are waiting there to get through the canal. You can see the irrigated farming areas there very, very nicely. All still on the same SAR image, we see Port Said. And then we can go all the way out into the Mediterranean Sea and see the other ships waiting for their turn to move through the Suez Canal. All on a single image taken from a tiny SAR satellite. And by the way, scan mode was not planned when these satellites were designed. It was thought of afterwards, and it became operational via a simple software upload to the satellite. Very easy. Flexible hardware, flexible software, tremendous innovation. So in our summary to our intro to SAR, we know that SAR penetrates clouds and darkness. It uses coherent illumination, and that means we can produce amplitude and phase pixels, both of them. And we can use the phase information for some advanced analysis. Resolution for SAR in both amplitude and phase is independent of distance. And we have multiple imaging modes. Spotlight mode, small areas, very high resolution. And that resolution is improving as the months pass by. And soon it will be at its practical maximum, much less than a meter in both dimensions. Strip mode, in which we get large, long strips at medium resolution, and scan mode. And that resolution is improving as well. Very, very large areas at modest resolution. So in our next talk, we'll discuss what SAR images look like. Thank you.